All right, welcome back to our third day in our chapter on power series, and we're going to introduce you to a topic called a Taylor polynomial, and this is by far one of my favorite ones. I'm so excited. I got goosebumps running down the back of my neck here tonight as I get ready for this one. But so far, what have we done so far here in these last couple of lessons? We've introduced you to what we call the generic power series, and the generic power series was very basic, and it kind of looked like this. We said that there's some function that is represented by the power series a sub n x to the nth power, and I want to keep in mind that there was an infinite number of terms in that polynomial. As we expanded that rascal out, the upper bound was infinity, so it just kept going on and on forever and ever. Then we introduced you to a very special kind of a power series called a geometric. And the geometric was pretty useful because it said as long as you could get your function to look something like this, something similar to that, then we could rewrite it as a power series x to the nth power. And then we expanded it out, and we got 1 plus x to the first plus x squared plus x cubed plus dot 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 plus x to the nth power plus dot dot dot. And again, there was an infinite number of terms. They just kept going on forever and forever and ever, and that's what created the perfect match. Well, in a day or two, we're going to introduce you to a Taylor series. Now, the trick is, before we jump all the way to a Taylor series, we're going to take a brief hiatus from series. And today we're going to slow down and we're going to talk just about something called the Taylor polynomial. And the big difference today is our Taylor polynomials are going to have a finite number of terms. And then we're going to graduate to a Taylor series where there's an infinite number of terms. So we're going to kind of tap the brakes and slow down just a whisker today. But there's still going to be plenty to talk about, no doubt. Now, as we get ready to dive in today, I want to establish our goals with Taylor polynomials. Our Taylor polynomials, our goal is to find a polynomial to approximate. Okay, and I want to emphasize the word approximate. Approximate, just so we're all on the same page, approximate means a lot like estimate. It means we're going to be very, very, very close, but it's not going to be an exact match, okay? So we're trying to approximate a transcendental function. Now, it kind of feels like we're going backwards, because a couple of days ago, we had these high-achieving goals of creating an exact perfect match. And we're not going to lose sight of that goal, and we're going to get back to that goal in a day or two. But like I said, we're tapping the brakes here today, and we're just working on approximating that function. And to summarize it, a Taylor polynomial has a finite number of terms, and therefore, because of the finite number of terms, it's only an approximation. But I want to emphasize, it will be a very good approximation. And then we're going to graduate to a Taylor series, which means, did I spell that wrong? Oh, goodness gracious. Taylor series. And now that you have a Taylor series, now that contains an infinite amount of terms, and now we have an exact match, a perfect match that matches our given function perfectly. Now, believe it or not, you've already done a first-degree Taylor polynomial. We just had different vocabulary for it. Back in September, we did a topic called local linearization, which was basically a fancy way of saying create a tangent line and use that tangent line to approximate a function. So what I want to do here is I want you to consider the function e to the x, just a very nice friendly one to start off with, and I want you to write the tangent line at x equals 0. Okay, so what would you do for that? This feels like we've jumped in our time machine and gone back to kindergarten basically. Well, you already know that f of 0 equals 1. Okay, so there's your y-coordinate. You know that the derivative of that function is still e to the x, therefore the slope at 0 is still 1. And if we put that all together, our tangent line would start to look like this. Normally we would stop right there, but today I just want to go ahead and solve for y, and we would get x plus 1. And maybe we'll even try to put this all together. We'll draw ourselves a little bit of a graph here. We know that e to the x behaves and looks like this. Okay, so there's my function. We'll switch colors here a little bit. Right there, that's when x equals 0, so I'm going to try to draw the best tangent line I can. All right. So there's your tangent line. And what you have right here is a first degree Taylor polynomial, believe it or not. And we're going to use the notation. We're going to call that P sub 1 of x. And that's our notation for a first degree Taylor polynomial, hence the subscript 1. So, and I'm going to replace that y with a P sub 1 of x right there. That's our first degree Taylor polynomial. And what you'll notice is, let me say this also. We consider this Taylor polynomial to be centered at x equals 0. Okay, let's put that in quotations. This polynomial is centered at x equals 0 because the tangent line touches the curve right at x equals 0. And we've used the terminology centered the last couple of days, but we really haven't talked about what it means, and we haven't been able to visualize it. And it's as simple as saying that's where the tangent line hits the curve. Now what you'll notice is if you stay relatively close to the point of tangency, then our polynomial does a really good job of approximating that function. But once you move further and further and further away from that point of tangency or the center, then the accuracy of our approximation greatly diminishes. So let's make sure we put that in words there in our notebook, that as we move further away from the center, the accuracy of our approximation decreases or diminishes typically. Okay. A few other things I want to talk about that are really important to note here is that f of x, the original function, and our first degree Taylor polynomial, they share two things in common. What do they share? Number one, they share the same value, aka y-coordinate at x equals 0. And number two, they share the same slope at x equals 0. Okay? And that's what makes it a good approximation at that point of tangency. Now, the goal all along has been to improve the accuracy of our approximation. And so that's the question we want to pose. How are we going to improve the accuracy of our approximation? How can we improve the accuracy of our approximation? Well, what we're going to do is we're going to impose yet another requirement. Okay? We are going to say, what if our original function and our polynomial shared the same second derivative values? What if they shared the same second derivative values? Of course, at x equals 0. Okay? So we already have the first two requirements met. Now we're going to impose a third requirement that not only do they have the same y value, not only do they have the same slope, but let's make sure they have the same concavity at that one moment in time and see if we can improve our approximation. Now here's what it might look like graphically if we up the ante from our first degree to our second degree Taylor polynomial. Now the first degree one here on the left is the one that we already did, and you'll notice maybe from here to here the tangent line does a really good job of approximating. So we're saying like maybe from -1/2 to +1/2, it does a good job. Now over here, and it's a little blurry, but hopefully you can see here that we put the second degree. Now you don't know how to build the second degree Taylor polynomial yet, but you will in a few minutes. And what we have here is you can follow this curve. It goes right here, and then it blends in, and it blends in, and then you could start to see it right there. What I traced there in red is the second degree polynomial, and you could see how the behavior is much closer to e to the x than the tangent line we had minutes ago. And I would say starting here it's a good match, up until here it's a good match. So we've increased what we would call our interval of convergence. And then you could kind of see where we're going with this. And you could say, well, you could up the ante again and say, how could we improve the accuracy of the second degree polynomial? And we could say, well, what if their third derivative values agreed at x equals 0? Then what if their fourth derivative values agreed at x equals 0? And so on and so on and so on. And we could create like a 10th degree Taylor polynomial or even a 100th degree Taylor polynomial. And what you would see is the accuracy would just continuously improve more and more each time. And as we took pictures, the curves would be perfect matches for larger intervals. All right, now to get to the meat and potatoes part of the lesson, we're going to talk specifically about Taylor's theorem, and it's going to look extremely intimidating the first time you see this, but if we practice it a little bit, you're going to find out that it's pretty friendly. Anyway, he says that the nth degree Taylor polynomial, and I'm a little bit nervous about fitting it on the screen, so I use a subscript of n to show that it's the nth degree, and it says it looks like this. F of c is the first term, plus f prime of c, whoops, that's a c right there. Very important that that's a c. Times the quantity x minus c. Now, if I stopped right there, what I have is a first degree Taylor polynomial, because the biggest derivative I've used is f prime, and a first degree Taylor polynomial is the same thing as a tangent line. Okay, so nothing exciting, nothing new so far. Until I add this term, the second derivative of c divided by 2 factorial times the quantity x minus c squared. Okay? Now it looks a little crazier. Then, right now, that's the second degree Taylor polynomial. If I add the next term, it would be the third derivative evaluated at c divided by 3 factorial times the quantity x minus c to the third. Plus, can you predict what the next term is going to be? It's going to be the fourth derivative, and I'm going to use Roman numerals, evaluated as c divided by 4 factorial times the quantity x minus c to the fourth power. And by now, I bet you've caught the pattern, and we could say that it's going to go all the way out to the nth derivative evaluated as c divided by n factorial times the quantity x minus c to the nth power. Now, I want you to put a big period at the end. What that period does is it emphasizes that there's a finite number of terms, not an infinite number of terms. And it emphasizes that it's a Taylor polynomial as opposed to a Taylor series. And that's going to be a big deal, especially on our free response questions on the AP exam. Now, right now, this particular polynomial is said to be centered at 0. Oh, geez, Louise, I take that back. It's centered at x equals c. I knew I said that wrong. Okay. Now, the most common, okay, by a mile, most convenient thing to do is to center these at x equals 0, just because it's easier to substitute a 0 in to evaluate all these derivatives as 0, as opposed to, to some other number like 5 or 6 or 7. So what we're going to do is we're going to simplify this and ask ourselves, what would it look like if I centered it at 0? In the nth degree Taylor polynomial would say f of 0 plus f prime of 0 times x minus 0. Okay, plus the second derivative evaluated at 0 divided by 2 factorial times x minus 0 squared. Let's see, plus the third derivative evaluated at 0 divided by 3 factorial times x minus 0 cubed. Whoa, that's supposed to be a 3. Looks like it tweaked out on us a little bit. Plus, I'm going to wrap it around just a little bit here. We've got the fourth derivative evaluated as 0 all over 4 factorial times the quantity x minus 0 to the fourth. Don't need those parentheses. Plus dot dot dot. Now we've got the nth derivative evaluated at 0 all over n factorial times x to the nth power, period. So this is what Taylor's theorem looks like centered at 0. And we have a special name for this one when it's centered at 0. Whenever this is centered at 0, we call it a Maclaurin polynomial instead of a Taylor polynomial, but it's still a Taylor polynomial basically. It's kind of like the relationship between Rolle's theorem and the mean value theorem. All right, so when we're centered at x equals 0, we now call it a Maclaurin, just another famous mathematician that we named it after. Okay, and this is important to know because the AP will use this guy's name quite often, and as soon as you see the word Maclaurin, you can automatically assume that it's centered at 0, and therefore, we kind of celebrate a little bit because we know that centered at 0 is usually typically easier than centering it at some other place like 2 or 3. Okay. It's going to be very important that we do memorize those general forms of the Taylor polynomial, both the one that's centered at c and then the Maclaurin version where it's centered at 0. And again, I know that sounds intimidating right now, but trust me, it'll be pretty easy once we get going. Those questions will be on our Monday bite-sized quizzes and so forth, and it'll be some of the easiest points you earn. Here's our first example. We're going to dive right in here and do an example. It says, find the nth degree Maclaurin polynomial for the function f of x equals e to the x power. Notice we've been starting with e to the x every time. He seems to be pretty friendly. One of the reasons he's so friendly is because the first derivative and the second derivative and the third derivative are so easy to compute. It's usually the first one we work with. Now, as far as building the nth degree, what I'm probably going to do is I'm going to build like the first 3 or 4 terms until I identify a pattern, and then once I feel confident about the pattern, I'll just kind of generalize it and write it in terms of n. And of course, this one we threw a Maclaurin at you, so we know we're centered at 0. The center is going to be at 0 here. So let's see. Here's how I organize my thoughts. I know that the original function is e to the x. I know the first derivative is e to the x. I know that the second derivative is e to the x. This seems a little redundant right now. I know the third derivative is also e to the x. What I'm going to do is I'm going to evaluate each of those derivatives at 0. So we know f of 0 is equal to 1. We know that the first derivative evaluated at 0 is 1. We know the second derivative evaluated at 0 is also 1. And we know the third derivative evaluated at 0 is equal to 1. So once we get all those derivatives evaluated at the point of center, we can now safely look back at our general form for our Maclaurin and just start plugging things in. And you're going to find out that this is pretty easy. Switch up colors here to make it a little more exciting maybe. So I'm going to say that the nth degree polynomial, let's see, the first term was a 1 plus, let's see, the first derivative times x. And then we've got the second derivative divided by 2 factorial times x squared. And then we've got the third derivative divided by 3 factorial times x cubed. And I bet you can kind of generalize the pattern that you see right now. And we could extend this all the way to the nth term and say, you know what, it's going to be 1 over n factorial times x to the nth power. Okay, and put that big period there for me, okay? That's something I do consider when I'm grading, especially on a spiral, is I want to see the period there, just to emphasize that there's a finite number of terms and not an infinite number of terms. And so we've constructed what we consider our nth degree Maclaurin polynomial. All right, time for our second example. They want us to find the 4th degree Taylor polynomial for the function natural log of x centered at x equals 1. Now, you might be thinking they're trying to make your life harder by centering it at 1 instead of 0. But here's one of those rare examples where both logically and so forth, it makes sense. We physically can't center it at 0 because the function natural log of x doesn't exist at 0. So that it wasn't an option to begin with. And what you're going to find out is, 1's probably the second easiest version because it's easy to evaluate all those derivatives at 1. And that's what I want to start off by doing. As far as I'm going to organize my thoughts the exact same way that I did on the previous example, where I'm just going to construct all of my derivatives. Okay? If you want to think of that as x to the negative 1, it might be helpful. My second derivative is going to be negative x to the negative 2. My third derivative is going to be positive 2x to the negative 3. And my fourth derivative, once I get to the fourth derivative, I start to use Roman numerals typically. And that's what my fourth derivative looks like. Now what I'm going to do is I'm going to come on back here and I'm going to evaluate all of these at 1. Let's see, natural log of 1 is 0. And then the first derivative evaluated at 1 is simply 1. The second derivative evaluated at 1 is going to be a negative 1. The third derivative evaluated at 1 is going to be a positive 2. Told you this was pretty easy. And then the fourth derivative evaluated at 1 is going to be a negative 6. So those are the values that we're going to plug into the Taylor polynomial. Now, make sure you're not thinking of a Maclaurin on this one. We've got to use the original Taylor polynomial here. Let's see, we'll change colors really quick. I'm going to say p sub 4 because it's a 4th degree. And the first term was just a 0, so you don't really have to write that, but I'm going to do that just for emphasis. And then we're going to say plus 1. Okay, times the quantity x minus 1 because we're centered. Whoops. I wrote c. Okay, I should be writing a 1 right there. Okay, then minus 1 over 2 factorial x minus 1 quantity squared plus, now the third derivative gave you a 2. Okay, so we're going to do 2 over 3 factorial x minus 1 cubed plus, and we got to squeeze in one more term here. When I evaluated the fourth derivative, I got negative 6 all over 4 factorial x minus 1 quantity to the fourth throw that big fat period at the end. And what we've created here is the 4th degree Taylor polynomial. Now what I want to do now is I'm going to import some pictures for us to look at. We're going to see and hopefully gain an appreciation for what a good job this function is doing at approximating the natural log of x. Okay, here's a couple pictures for us to look at. The first picture is not that exciting. All we have here is the 1st degree Taylor polynomial if we stopped right there. And it does a pretty good job of approximating within a short interval. And then over here we've got the 2nd degree Taylor polynomial. You'll notice it does a better job of mimicking the behavior of our original function, natural log of x. And I would say from here till about there, it does a really good job of imitating its values. And then we're going to see, okay, let's compare that to the 3rd degree polynomial here. The 3rd degree polynomial curves in this nature here. Does a really good job from like there to there. And then one more time, we stopped with the 4th degree, and the picture's not as clear as I wish it was, but I think it still serves its purpose. You notice how good it does before it really breaks away. So as long as we stayed from here to here, it did a really good job of mimicking the behavior of our original function, natural log of x. And you can only imagine if we took a little more time and went to maybe the 5th, 6th, or 7th degree polynomial, how much of a better job it would do. And of course, we can imagine using a computer software program where we went to the 100th degree, maybe the 1000th degree, maybe the 1,000,000th degree polynomial. And what an amazing job that polynomial would do at mimicking this transcendental function. Okay, we're going to finish up here. Our 3rd example is going to be our final one of the night, and it's my favorite one, especially the graph we look at the end. I think it does a spectacular job. But we're going to create the 6th degree Maclaurin polynomial for the function cosine of x. All right. Of course, as soon as you see that word Maclaurin, we know that it's going to be centered at 0, and that's good news typically. Boy, 6th degree sounds intimidating. You're like, wow, I've got to do 6 derivatives? Are you kidding me? Well, what we're going to do is we're going to quickly identify a pattern, hopefully. We know that the first derivative is going to be negative sine. Okay, we know that the second derivative is going to be negative cosine. We know that the third derivative is going to be, let's see, positive sine. And then the 4th derivative is back where we started because of its cyclic behavior with cosine, okay? So what I'm going to do is I'm going to kind of skip the 5th and the 6th derivatives because I think I'm going to see a pattern by the time I get there. So if I evaluate the original function at 0, cosine of 0 is 1. Let's see, the sine of 0 is strictly 0. Of course, the negative doesn't change that. The second derivative of 0 is going to be negative 1. The third derivative evaluated as 0 is going to be 0. The 4th derivative evaluated as 0 is going to be back to 1. And so what you can kind of see here is that the 5th derivative evaluated as 0 is going to be 0. And then the 6th derivative evaluated as 0. Hopefully you can see that that's going to be the same as the second derivative and therefore be a negative 1. If we wanted to keep going, we know that the 7th derivative would be 0 and that the 8th derivative would be positive 1, so forth and so forth. So one of the reasons that I like sine and cosine so much is because we could easily do the 20th degree Maclaurin polynomial for cosine with little effort. So let's go ahead and see if we can put this all together now, knowing what these values are. All right, the 6th degree, so I got p sub 6 of x. Let's see, the first term turned out to be a 1. Now, the first derivative produced a 0, so that pretty much obliterates and blows up that entire term. I'm going to skip that entire term. And I'm going to fast forward right to the second derivative, which was negative 1. It has to be divided by 2 factorial, and it's going to be x minus 0 squared. Of course, those parentheses aren't required. The next term after that, let's see, the third derivative produced a 0, so it's going to totally blow up that term. I'm going to skip it completely, and I'm going to fast forward to the next term. 1 over 4 factorial, and then x minus 0 to the 4th power. I'm going to skip the 5th term, because the 5th derivative evaluated as 0 was 0. And now I've got minus 1 all over 6 factorial times x to the 6th. Let's throw a big period there. So even though it was a 6th degree Taylor polynomial, my answer only contains 4 terms because a bunch of them dropped out because of the 0. Now, do you remember back in pre-calc when we talked about symmetry? Do you remember when we said that cosine of x was described as an even function. It had even symmetry, we said, because it was symmetric with respect to that y-axis, and it looked something like this. Do you remember that? Well, everything's kind of coming full circle here today, because if you look at the Taylor polynomial, each term within the Taylor polynomial consists of an even exponent. All the odd exponent terms got canceled out. So it's kind of, that's how I remember what cosine's Maclaurin polynomial looks like, because it has only even terms in it. Now we're going to finish off. I'm going to import one more picture for you, and it looks like this. Once again, it's a little blurrier than I wish it was, but it's got the original cosine curve, and then it's got our 6-degree Taylor polynomial laid right on top of it. And our 6-degree Taylor polynomial looks just like this. You can faintly see it here. It goes boom, 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 laying perfectly, and then right there it starts to pull away a little bit. And so we would say all the way from approximately negative pi all the way almost to positive pi, our 6-degree Taylor polynomial is a great approximation for the original curve. And of course, like I said, we could go all the way to the 20th degree, maybe the 40th degree without much effort at all, and you'd be amazed at the accuracy of our approximation. So today's theme is Taylor polynomials. There's a finite number of terms, and therefore it's only an approximation. We're not quite satisfied yet. We're going to take it, hopefully we're going to make our Taylor series have an infinite number of terms in the next couple of days, and they'll be perfect matches.